Professor D.D. Sharma will talk about photoelectron spectroscopy, photon emission processes. And so what I would like to do is to in fact just set up the very fundamental basic ideas of what you measure. Okay? Not how you measure, that will be discussed in detail by Dr. Sharma. Even what you measure in detail will also be there in his talks, but just from very fundamental quantum mechanical point of view, what you do in photoelectron spectroscopy. And I will see, as you will see, that the methodology you use is in fact not dissimilar to most measurements you make. So how do you make measurements? You want to know something about a system. So how do you know, or how do you know something about a system? So you have to perturb it. Right? If I want to know how strong the wood is, I'll hit it with my hand and see how the wood responds. So this hitting is done in wherever light is involved, like lasers. Then you hit it with light. And your system is now basically a system of electrons because we're interested in the electronic structure of materials. So the question therefore is, how does light interact with this system of electrons, and how, by either looking at absorption or emission or scattering, you can find out properties of the system at hand. Therefore, you also feel that you should not perturb the system too much, because if you do perturb it too much, then you would, of course, change the property of the system. That is, intrinsic property of the system. Of course, you do such things, called nonlinear spectroscopy, where you look at nonlinear effects, or strongly viscous medium, where things can even flow plasticity, like a plastic glassy system, we apply little stress, the things start flowing. These are all the things we are concerned with. We are concerned with phenomena and experiments in which this perturbation is weak. And this is what is called a linear response. Now, though I talk, because of Sharma's lecture, in terms of interaction of photons, the light with a system of electrons, you see similar phenomena anywhere, like for instance nuclear magnetic resonance or electron spin resonance, where instead of the laser field, like for instance in NMR, you have a radio frequency field that you apply, so which is also an electromagnetic field. And there the system, of course, like in the case of NMR, is the nuclear spin, the proton spin, for instance, biology, water, everywhere. So your system then is a bunch of spins. In our case, the system is a bunch of electrons, and the incident beam is that of a photon. So when in NMR or ESR, it is the same phenomenon, except that you use microwave because of the fact that Bohr magneton is different from the nuclear magneton by 3 orders of magnitude. So, and you cause energy level separation by the application of an external magnetic field in NMR, what's called the Zeeman. So here, we don't have such an external field. Of course, we can also do in-field experiments, but basically you want to have photons all on it. So this goes back to the simple photoelectric effect that you've all seen in your high school days, that if you have a metal, so remember photoelectric effect, and it is the explanation of this effect along with black body radiation that earned Einstein the Nobel Prize in Physics, not in 1905, the discovery is in the theory is in 1905, the experiments were in actually 3 years earlier, and prize in fact came some 15, 16 years later, that you have a piece of metal and you have light falling on it, so you have a photon, h nu, which can also write as h bar omega, you know this notation, right? And what you do is you eject an electron Now the electrons are of course bound to the metal, and so in order to overcome that binding, you have to give energy. So that's how that the energy comes from this. So the emitted electron will move with a kinetic energy, and in addition you need the binding energy, which is called the work function. Right? This is a simple photoelectric effect. Now in photo emission, you have the same thing doing actually in a more sophisticated version that Sharma will talk about in detail. So you have a system of electrons, maybe in an atom or a molecule or a tight binding lattice or whatever, or graphene, and you have light falling on it. Okay? Now suppose I have a single electron. Let's do that problem first. So I have a single electron, and I want to know what is the interaction between this incoming photon field or the electromagnetic field with this electron. Do you know? Suppose I have an electron moving with a certain momentum, and I shine electromagnetic field. What will happen? Any guess? What happens to charged particles moving? Huh? Hey, what will be the
transition
interaction, the Hamiltonian, that is? Simple interaction Hamiltonian. What will be that? Let's say, so the electron, okay, this is Hamilton. Electron initially has a kinetic energy, right? You write it as p squared over 2m. M is the mass of the electron, right? So now I shine electromagnetic radiation. What happens?
there will be interaction.
So what is that interaction?
You don't
Have you seen vector potential in any class? Huh? Yeah. Okay, so tell me, I have an electron. So suppose I put an electron in a magnetic field. I put an electron in an electric field. What happens? This is high school stuff. I put an electron in an electric field of intensity E. What happens?
will experience the force.
It experiences a force. Very good. And that force is given by the charge of the electron, that's the electric field. Electric field is a gradient of a potential, correct? हाँ? तो Ohm's law में सब जगह देखा. हाँ, अच्छा. Now I have a magnetic field. What happens? Huh?
Lorentz force.
Lorentz force. Ritika, you have not seen Lorentz force? Huh? School में लगा ना. So electrostatic interaction. Electrostatic is E times T, and magnetic is, somebody will tell me? This is coming from Mittika. So this is due to Mr. Lorentz, right? This is Coulomb, right? Okay. Now I want to put both of them together in one formulation. What do I do? Somebody must have seen this. Okay, let me do it and then ask you how many of you have still with that. Now, Goldstein chapter 1, classical mechanics. Do you remember? What happens to the Lagrangian of a charged particle in a magnetic electromagnetic field? So, Maxwell's equations. What are Maxwell's equations? So far we have not seen magnetic monopoles, right? So, let's go back to Maxwell's equation. So, suppose I have no magnetic charge. How do I describe this? There is no magnetic charge.
Divergence of B is equal to 0.
Very good. Divergence of B is equal to 0. If B is equal to 0. Okay. Similarly, divergence of E would be where free charges.
4 by
4 pi or whatever, you use various of these units today. So it goes like charge density. I'm not writing the other ones. So if divergence of B equal to 0, does it say anything about the property of that field B? If divergence of any vector is equal to 0, then that vector
is represented as
is a curl of another vector, correct? So this says, therefore, I can write B as a curl of a vector B, because there is a property that, well, curl, since I am using this notation, you write it as curl of A. So the property is that if some vector, you have the curl of a vector, then the divergence of that vector is equal to 0. But it has got a remarkable, this relation tells you something more remarkable, is that, now what can I do to this curl of A? Suppose I add to this A grad of another scalar. I get a vector, right? What happens?
It won't affect anything.
It won't affect because there's a property that curl of grad is identically equal to 0. Madam, and all these people, you please work it out at home. No? I mean, this is simple high school stuff. But if you have not seen it, you see what happens is unfamiliarity actually creates a fear. And that fear you should not have. So just familiarize yourself, because otherwise, what is the point of, take a nanomaterial or take graphene or take fullerene and you do photoelectron spectroscopy? You might be routinely doing that in the laboratory, but you have to have some basic understanding of it. This is why in IICR, the first 2 years we want to teach all courses to all students on equal footing. And these things come in the first 2 years itself. I don't know, people can correct me. So this, do you know what is this called? There's a fancy name that you can add to the vector potential the grad of a scalar and still get the same physical field, because this is a physical field. A is not like a physical field. This is like the wave function in quantum mechanics. The wave function is normally not measurable because the phase of the wave function rather, because the wave function, the Schrödinger wave function psi has an amplitude and a phase, like Sharma was talking yesterday, e to the I k naught r kind of thing. These are phase factors. Okay. Now, why is it not physical? The phase or physically measurable? Because you're always looking at the mod psi squared to calculate the probability density. When you do the mod psi, e to the ikr, e to the minus ikr, when you do the complex conjugate, e to the ikr disappears. The only way to see the phase is do what?
Interference.
Huh?
Interference experiment.
Absolutely. So you do interference. This is precisely what you do in optics, right? The double slit experiment. So what we are talking about is very similar to optics, because of course light is electromagnetic radiation. And so everything about Schrödinger quantum mechanics has its phase properties, interference, etc. They're all there. Okay, so what time does your lecture start? At 10:30 is the tea break.
Yeah.
Okay, all right. So we should follow that schedule because we have to leave in the afternoon. Okay, so vector potential is also like this, that is not directly measurable. Okay, and in fact I am spending more time on it because I had planned to do tomorrow morning what is called the Aharonov bomb effect, where you actually show how by application of a magnetic field to the tight binding model that Sharma was talking about, the magnetic field comes into the phase of those terms which he called T. From today onwards I'll also call it T, not J, the hopping term. The hopping term acquires a phase due to the electromagnetic field, and that's due to the something remarkable phenomenon called the Aharonov bomb effect. And you do interference experiments, okay? And you can do that in something like a ring, a mesoscopic ring, where there's few sides coupled by tight binding, hopping, and see how the phase is actually physically measurable. So it's a combination of electromagnetic theory and quantum mechanics makes the Aronoff-Bohm effect observable in the laboratory. And Professor Chiranjeev Mitra will tell you more about it because these things are routinely used now to look at quantum coherence and quantum computing. These are buzzwords, but you must have also the buzzwords in your mind because that is where exciting things are happening. Yet at the same time, I'm an old man, so please don't mind my saying this over and over again, that don't forget the basics. Okay? This is called IISR, Indian Institute of Science Education and Research. So this is very important to keep that in mind. All right. So now, I will say things now in words. That if you use this Hamiltonian and you write down equations of motion, what are the equations of motion in classical mechanics? See, you have to ensure that with this structure, Ampere knew about it. With this structure, if you write equations of motion, you will discover that in fact in the equations of motion appear a Lorentz force term. See, normally Newton's equation says that mass times inertia is the external force. Now, if I have an electric field, that force, I'm not worried about it. I mean, if you put in charge E to be negative, there will be a negative sign maybe. Plus, you must have this Lorentz force coming in. Oh, there's no charge. So you must ensure this, because this is your sacrosanct equation of motion. It's Newton's equation. But now, because of the magnetic field, a new entity has appeared. This is a very fascinating stuff, actually, because the first time you encounter, in the first chapter of Goldstein, I'm saying, repeating, at least the physics people must have seen the first chapter of Goldstein. Okay? And even the chemistry people, I mean, they're all over, you know. I have a book called Atkins, Physical Chemistry. It has everything in quantum mechanics. Why don't you read Atkins? Why is it remarkable? Because the first time you saw that there's a velocity-dependent potential appearing in the formula, right? Because right-hand side is a force is derivable as a gradient of a potential, so it's a velocity-dependent potential. Normally, your force is not velocity-dependent unless you bring in friction. Like for instance, you could drop a ball through a liquid jar, you get frictional force, that's Stokes' force is velocity. Normally, but here is a friction, and therefore, this equation actually normally you would say that there's a problem with time reversal invariant because if you change t to minus t, the left hand side doesn't change because dt is squared, you square it, it will change. This term doesn't change, but velocity v will change sign. So what do you have to do to restore time reversal invariance? Because your fundamental equation must obey this time symmetry. And what do you have to do this? Actually, you ask magnetic property measurement system expert, but his system doesn't function anymore, he told me in the morning, that you have, whenever you have a magnetic field, it comes from actually a current coil. So, if you change the time t to minus t, that coil will also create a magnetic field in a different direction. So that's the time reversal. So anyway, so that's there in this. Now you expand it. And you get this term, which is the free kinetic energy of the electron. They're freely moving, let us say. Okay? And you have terms 1 over m c e by mc p dot e in, and a term which is quadratic in a. Now it is this term that you drop because of what I said, linear absorption, linear response, U shining both beam of photons and the electron system, and you want to only look at